History. In 1979, Bjarne Stroustrup, a Danish computer scientist, began work on C with classes, the predecessor to C++. The motivation for creating a new language originated from Stroustrup's experience in programming for his PhD thesis. Stroustrup found that Simula had features that were very helpful for large software development, but the language was too slow for practical use, while BCPL was fast but too low-level to be suitable for large software development. When Stroustrup started working in AT&T Bell Labs, he had the problem of analyzing the Unix kernel with respect to distributed computing. Remembering his PhD experience, Stroustrup set out to enhance the C language with Simula-like features. C was chosen because it was general-purpose, fast, portable and widely used. As well as C and Simula's influences, other languages also influenced this new language, including ALGOL 68, Ada, CLU and ML. Initially, Stroustrup's C with classes added features to the C compiler, CPRE, including classes, derived classes, strong typing, inlining and default arguments. In 1982, Stroustrup started to develop a successor to C with classes, which he named C++ after going through several other names. New features were added, including virtual functions, function name and operator overloading, references, constants, type-safe free store memory allocation, improved type checking, and BCPL-style single-line comments with 2 forward slashes. Furthermore, Stroustrup developed a new, stand-alone compiler for C++, Front. In 1984, Stroustrup implemented the first stream input/output library. The idea of providing an output operator rather than a named output function was suggested by Doug McElroy. In 1985, the first edition of the C++ programming language was released, which became the definitive reference for the language, as there was not yet an official standard. The first commercial implementation of C++ was released in October of the same year. In 1989, C++ 2.0 was released, followed by the updated second edition of the C++ programming language in 1991. New features in 2.0 included multiple inheritance, abstract classes, static member functions, const member functions, and protected members. In 1990, the annotated C++ reference manual was published. This work became the basis for the future standard. Later feature additions included templates, exceptions, namespaces, new casts, and a Boolean type. In 1998, C++ 98 was released, standardizing the language, and a minor update was released in 2003. After C++ 98, C++ evolved relatively slowly until, in 2011, the C++ 11 standard was released, adding numerous new features, enlarging the standard library further, and providing more facilities to C++ programmers. After a minor C++ 14 update released in December 2014, various new additions were introduced in C++ 17. After becoming finalized in February 2020, a draft of the C++ 20 standard was approved on September 4, 2020 and officially published on December 15, 2020. On January 3, 2018, Stroustrup was announced as the 2018 winner of the Charles Stark Draper Prize for Engineering, for conceptualizing and developing the C++ programming language. As of 2022, C++ ranked 4th on the SHIOB Index, a measure of the popularity of programming languages, after Python, C, and Java. Etymology. According to Stroustrup, the name signifies the evolutionary nature of the changes from C. This name is credited to Rick Mashity and was first used in December 1983. When Mashity was questioned informally in 1992 about the naming, he indicated that it was given in a tongue-in-cheek spirit. The name comes from C's ++ operator and a common naming convention of using plus to indicate an enhanced computer program. During C++'s development period, the language had been referred to as New C and C with classes before acquiring its final name. Philosophy. Throughout C++'s life, its development and evolution has been guided by a set of principles. It must be driven by actual problems and its features should be immediately useful in real-world programs. Every feature should be implementable. Programmers should be free to pick their own programming style, and that style should be fully supported by C++. Allowing a useful feature is more important than preventing every possible misuse of C++. It should provide facilities for organizing programs into separate, well-defined parts, and provide facilities for combining separately developed parts. No implicit violations of the type system. User-created types need to have the same support and performance as built-in types. Unused features should not negatively impact created executables. There should be no language beneath C++. C++ should work alongside other existing programming languages, rather than fostering its own separate and incompatible programming environment. If the programmer's intent is unknown, allow the programmer to specify it by providing manual control. Standardization. C++ is standardized by an ISO working group known as JTC1/SC22/WG21. So far, it has published 6 revisions of the C++ standard and is currently working on the next revision, C++23. In 1998, the ISO working group standardized C++ for the first time as ISO/IEC 14882:1998, which is informally known as C++ 98. In 2003, it published a new version of the C++ standard called ISO/IEC 14882:2003, which fixed problems identified in C++ 98. The next major revision of the standard was informally referred to as C++ 0x, but it was not released until 2011. C++ 11 included many additions to both the core language and the standard library. In 2014, C++ 14 was released as a small extension to C++ 11, featuring mainly bug fixes and small improvements. The draft international standard ballot procedures completed in mid-August 2014. After C++ 14, a major revision C++ 17, informally known as C++ 1z, was completed by the ISO C++ committee in mid-July 2017 and was approved and published in December 2017. As part of the standardization process, ISO also publishes technical reports and specifications. ISO/IEC TR 18015:2006 on the use of C++ in embedded systems and on performance implications of C++ language and library features. ISO/IEC TR 19768:2007 on library extensions mostly integrated into C++ 11. ISO/IEC TR 29124:2010 on special mathematical functions, integrated into C++ 17. ISO/IEC TR 24733:2011 on decimal floating point arithmetic. ISO/IEC TS 18822:2015 on the standard file system library, integrated into C++ 17. ISO/IEC TS 19570:2015 on parallel versions of the standard library algorithms, integrated into C++ 17. ISO/IEC TS 19841:2015 on software transactional memory. ISO/IEC TS 19568:2015 on a new set of library extensions, some of which are already integrated into C++ 17. ISO/IECTS 19217:2015 on the C++ concepts, integrated into C++ 20. ISO/IECTS 19571:2016 on the library extensions for concurrency, some of which are already integrated into C++ 20. ISO/IECTS 19568:2017 on a new set of general-purpose library extensions. ISO/IECTS 21425:2017 on the library extensions for ranges, integrated into C++ 20. ISO/IECTS 22277:2017 on coroutines, integrated into C++ 20. ISO/IECTS 19216:2018 on the networking library. ISO/IECTS 21544:2018 on modules, integrated into C++ 20. ISO/IECTS 19570:2018 on a new set of library extensions for parallelism. ISO/IECTS 23619:2021 on a new extensions for reflection. More technical specifications are in development and pending approval, including new set of concurrency extensions. Language. The C++ language has two main components: a direct mapping of hardware features provided primarily by the C subset, and zero overhead abstractions based on those mappings. Strup describes C++ as a lightweight abstraction programming language for building and using efficient and elegant abstractions, and offering both hardware access and abstraction is the basis of C++. Doing it efficiently is what distinguishes it from other languages. C++ inherits most of C's syntax. The following is Bjarne Strup's version of the Hello World program that uses the C++ standard library stream facility to write a message to standard output. Object storage. As in C, C++ supports four types of memory management: static storage duration objects, thread storage duration objects, automatic storage duration objects, and dynamic storage duration objects. Static storage duration objects. Thread storage duration objects. Automatic storage duration objects. Dynamic storage duration objects. Templates. C++ templates enable generic programming. C++ supports function, class, alias, and variable templates. Templates may be parameterized by types, compile time constants, and other templates. Templates are implemented by instantiation at compile time. To instantiate a template, compilers substitute specific arguments for a template's parameters to generate a concrete function or class instance. Some substitutions are not possible. These are eliminated by an overload resolution policy described by the phrase "substitution failure is not an error." Templates are a powerful tool that can be used for generic programming, template metaprogramming, and code optimization, but this power implies a cost. Template use may increase code size, because each template instantiation produces a copy of the template code, one for each set of template arguments. However, this is the same or smaller amount of code that would be generated if the code was written by hand. This is in contrast to runtime generics seen in other languages where at compile time the type is erased and a single template body is preserved. Templates are different from macros. While both of these compile time language features enable conditional compilation, templates are not restricted to lexical substitution. Templates are aware of the semantics and type system of their companion language, as well as all compile-time type definitions, and can perform high-level operations including programmatic flow control based on evaluation of strictly type-checked parameters. Macros are capable of conditional control over compilation based on predetermined criteria, but cannot instantiate new types, recurse, or perform type evaluation, and in effect are limited to pre-compilation text substitution and text inclusion/exclusion. In other words, macros can control compilation flow based on predefined symbols but cannot, unlike templates, independently instantiate new symbols. Templates are a tool for static polymorphism and generic programming. In addition, templates are a compile-time mechanism in C++ that is Turing-complete, meaning that any computation expressible by a computer program can be computed, in some form, by a template metaprogram prior to runtime. In summary, a template is a compile-time parameterized function or class written without knowledge of the specific arguments used to instantiate it. After instantiation, the resulting code is equivalent to code written specifically for the passed arguments. In this manner, templates provide a way to decouple generic, broadly applicable aspects of functions and classes from specific aspects without sacrificing performance due to abstraction. Objects. C++ introduces object-oriented programming features to C. It offers classes, which provide the four features commonly present in OOP languages: abstraction, encapsulation, inheritance, and polymorphism. One distinguishing feature of C++ classes compared to classes in other programming languages is support for deterministic destructors, which in turn provide support for the resource acquisition as initialization concept. Encapsulation. Inheritance. Operators and operator overloading. C++ provides more than 35 operators, covering basic arithmetic, bit manipulation, indirection, comparisons, logical operations, and others. Almost all operators can be overloaded for user-defined types, with a few notable exceptions such as member access as well as the conditional operator. The rich set of overloadable operators is central to making user-defined types in C++ seem like built-in types. Overloadable operators are also an essential part of many advanced C++ programming techniques, such as smart pointers. Overloading an operator does not change the precedence of calculations involving the operator, nor does it change the number of operands that the operator uses. Overloaded end operators lose their short-circuit evaluation property. Polymorphism. Polymorphism enables one common interface for many implementations, and for objects to act differently under different circumstances. C++ supports several kinds of static and dynamic polymorphisms, supported by the language features described above. Compile-time polymorphism does not allow for certain runtime decisions, while runtime polymorphism typically incurs a performance penalty. Static polymorphism. Dynamic polymorphism. Inheritance. Virtual member functions. Lambda expressions. C++ provides support for anonymous functions, also known as lambda expressions, with the following form. Since C++20, you can write template parameters on a lambda without the keyword template. If the lambda takes no parameters, and no return type or other specifiers are used, the can be omitted, that is, the return type of a lambda expression can be automatically inferred, if possible, e.g. The list supports the definition of closures. Such lambda expressions are defined in the standard as syntactic sugar for an unnamed function object. Exception handling. Exception handling is used to communicate the existence of a runtime problem or error from where it was detected to where the issue can be handled. It permits this to be done in a uniform manner and separately from the main code, while detecting all errors. Should an error occur, an exception is thrown, which is then caught by the nearest suitable exception handler. The exception causes the current scope to be exited, and also each outer scope until a suitable handler is found, calling in turn the destructors of any objects in these exited scopes. At the same time, an exception is presented as an object carrying the data about the detected problem. Some C++ style guides, such as Google's, LLVMs, and Qt's, forbid the usage of exceptions. The exception-causing code is placed inside a try block. The exceptions are handled in separate catch blocks. Each try block can have multiple exception handlers, as it is visible in the example below. It is also possible to raise exceptions purposefully, using the throw keyword. These exceptions are handled in the usual way. In some cases, exceptions cannot be used due to technical reasons. One such example is a critical component of an embedded system, where every operation must be guaranteed to complete within a specified amount of time. This cannot be determined with exceptions, as no tools exist to determine the maximum time required for an exception to be handled. Unlike signal handling, in which the handling function is called from the point of failure, exception handling exits the current scope before the catch block is entered, which may be located in the current function or any of the previous function calls currently on the stack. Enumerated types. Standard library. The C++ standard consists of two parts, the core language and the standard library. C++ programmers expect the latter on every major implementation of C++. It includes aggregate types, algorithms, input/output facilities, file system library, localization support, smart pointers for automatic memory management, regular expression support, multi-threading library, atomic support, time utilities, a system for converting error reporting that doesn't use C++ exceptions into C++ exceptions, a random number generator, and a slightly modified version of the C standard library. A large part of the C++ library is based on the standard template library. Useful tools provided by the STL include containers as the collections of objects, iterators that provide array-like access to containers, and algorithms that perform operations such as searching and sorting. Furthermore, maps and sets are provided, all of which export compatible interfaces. Therefore, using templates, it is possible to write generic algorithms that work with any container or on any sequence defined by iterators. As in C, the features of the library are accessed by using the number include directive to include a standard header. The C++ standard library provides 105 standard headers, of which 27 are deprecated. The standard incorporates the STL that was originally designed by Alexander Stepanov, who experimented with generic algorithms and containers for many years. When he started with C++, he finally found a language where it was possible to create generic algorithms that perform even better than, for example, the C standard library XORT, thanks to C++ features like using inlining and compile time binding instead of function pointers. The standard does not refer to it as STL, as it is merely a part of the standard library, but the term is still widely used to distinguish it from the rest of the standard library. Most C++ compilers, and all major ones, provide a standards-conforming implementation of the C++ standard library. C++ Core Guidelines. The C++ Core Guidelines are an initiative led by Bjarne Stroustrup, the inventor of C++, and Herb Sutter, the convener and chair of the C++ ISO working group, to help programmers write modern C++ by using best practices for the language standards C++ 11 and newer, and to help developers of compilers and static checking tools to create rules for catching bad programming practices. The main aim is to efficiently and consistently write type and resource-safe C++. The core guidelines were announced in the opening keynote at CPPCon 2015. The guidelines are accompanied by the Guideline Support Library, a header-only library of types and functions to implement the core guidelines and static checker tools for enforcing guideline rules. Compatibility. To give compiler vendors greater freedom, the C++ Standards Committee decided not to dictate the implementation of name mangling, exception handling, and other implementation-specific features. The downside of this decision is that object code produced by different compilers is expected to be incompatible. There were, however, attempts to standardize compilers for particular machines or operating systems, though they seem to be largely abandoned now. With C, C++ is often considered to be a superset of C, but this is not strictly true. Most C code can easily be made to compile correctly in C++, but there are a few differences that cause some valid C code to be invalid or behave differently in C++. For example, C allows implicit conversion from void asterisk to other pointer types, but C++ does not. Also, C++ defines many new keywords, such as new and class, which may be used as identifiers in a C program. Some incompatibilities have been removed by the 1999 revision of the C standard, which now supports C++ features such as line comments and declarations mixed with code. On the other hand, C99 introduced a number of new features that C++ did not support that were incompatible or redundant in C++, such as variable length arrays, native complex number types, designated initializers, compound literals, and the restrict keyword. Some of the C99 introduced features were included in the subsequent version of the C++ standard, C++11. However, the C++11 standard introduces new incompatibilities, such as disallowing assignment of a string literal to a character pointer, which remains valid C. To intermix C and C++ code, any function declaration or definition that is to be called from / used both in C and C++ must be declared with C linkage by placing it within an extern C / block. Such a function may not rely on features depending on name mangling. Criticism. Despite its widespread adoption, some notable programmers have criticized the C++ language, including Linus Torvalds, Richard Stallman, Joshua Bloch, Ken Thompson, and Donald Knuth. One of the most often criticized points of C++ is its perceived complexity as a language, with the criticism that a large number of non-orthogonal features in practice necessitates restricting code to a subset of C++, thus eschewing the readability benefits of common style and idioms. As expressed by Joshua Bloch, I think C++ was pushed well beyond its complexity threshold, and yet there are a lot of people programming it. But what you do is you force people to subset it. So almost every shop that I know of that uses C++ says, yes, we're using C++, but we're not doing multiple implementation inheritance and we're not using operator overloading. There are just a bunch of features that you're not going to use because the complexity of the resulting code is too high. And I don't think it's good when you have to start doing that. You lose this programmer portability where everyone can read everyone else's code, which I think is such a good thing. Donald Knuth, who said of Edsger Dijkstra that to think of programming in C++ would make him physically ill, the problem that I have with them today is that C++ is too complicated. At the moment, it's impossible for me to write portable code that I believe would work on lots of different systems, unless I avoid all exotic features. Whenever the C++ language designers had two competing ideas as to how they should solve some problem, they said okay, we'll do them both. So the language is too baroque for my taste. Ken Thompson, who was a colleague of Strastrup at Bell Labs, gives his assessment, it certainly has its good points. But by and large I think it's a bad language. It does a lot of things half well and it's just a garbage heap of ideas that are mutually exclusive. Everybody I know, whether it's personal or corporate, selects a subset and these subsets are different. So it's not a good language to transport an algorithm to say, I wrote it. Here, take it. It's way too big, way too complex. And it's obviously built by a committee. Strastrup campaigned for years and years and years, way beyond any sort of technical contributions he made to the language, to get it adopted and used. And he sort of ran all the standards committees with a whip and a chair. And he said no to no one. He put every feature in that language that ever existed. It wasn't cleanly designed, it was just the union of everything that came along. And I think it suffered drastically from that. However, Brian Kernighan, also a colleague at Bell Labs, disputes this assessment. C++ has been enormously influential. Lots of people say C++ is too big and too complicated, etc., but in fact it is a very powerful language, and pretty much everything that is there for a really sound reason. It is not somebody doing random invention, it is actually people trying to solve real-world problems. Now a lot of the programs that we take for granted today, that we just use, are C++ programs. Strastrup himself comments that C++ semantics are much cleaner than its syntax. Within C++, there is a much smaller and cleaner language struggling to get out. Other complaints may include a lack of reflection or garbage collection, long compilation times, perceived feature creep, and verbose error messages, particularly from template metaprogramming. See also: comparison of programming languages, list of C++ compilers, outline of C++, category C++ libraries.